for my video project, I had project 28, which was a two-part project. Part 1, which is stated here, which says, sketch the region enclosed by the curve y equals square root of x minus 1 and x minus y equals 1 and find its area. So from that, I just rewrote the two functions with two arbitrary letters that represent the functions f of x and then g of x. So because x minus y equals 1 is not in its most standard form of y equals mx plus b, I just subtracted x and then divided by -1 on both sides to give you y equals x minus 1, or in this case g of x equals x minus 1. And then after that, I sketched the two functions, which you can see here, and then I shaded the area between the two curves. So mathematically, to find this area that I shaded in blue, you have to take the definite integral of both of them and subtract it, or subtract the two definite integrals of each curve. And to first find the bounds of those two curves, you have to solve for where they intersect, which is shown here. So I rewrote the two functions, you can see at the top, and then I set them equal to each other. And the first thing that I did when doing so is I squared both sides to remove the square root on the left. In doing so, you have the quantity of x minus 1 squared, which you have to rewrite as x minus 1 times x minus 1, which is x squared minus 2x plus 1. So then I set x minus 1 equal to x squared minus 2x plus 1, added 1 to both sides, as well as subtracted x on both sides to give you 0 equals x squared minus 3x plus 2. Now, I use the quadratic equation to solve for the two x values. There is definitely a simpler way to do that I just chose not to do. So using the quadratic equation, you can see that it is shown here, which is negative b plus or minus the square root of b squared minus 4ac all over 2a. I plugged in the respective values for a, b, and c, which are the coefficients of x squared, or the coefficients of each x value. So for x squared, the coefficient is 1. For x, it's -3, and then for 2, x to the 0 power is just 2, which is the c value. So plugging them in, you get -1 times -3 plus or minus the quantity of plus or minus the square root of -3 squared minus 4 times 1 times 2 all over 2 times 1, which can be rewritten and simplified into 3 plus or minus the square root of 9 minus 8, which is just -4 times 1 times 2, divided by 2, which again can be even simplified again to 3 plus or minus square root of 1 over 2, and we know that square root of 1 is just 1, so that equals 3 plus or minus 1 over 2, which is just 3 plus 1, which you have to break into two parts of 3 plus 1 over 2 and 3 minus 1 over 2. And for those two respective equations, you get 2 and 1. So now we found the x values for where those two curves intersect. And then to find the y values, you just pick either of the functions and plug in the x values. I picked g of x's function because it's easier, it's just x minus 1. So I did g of 1 equals 1 minus 1, which is 0. So for the first intersection point, it's 1 comma 0. And then I did g of 2, which is g of 2 equals 2 minus 1, which is just 1. So the other intersection point is 2 comma 1, which you can see that I drew them on the graph. 1 comma 0 and 2 comma 1, which is where these two functions intersect, which gives us the bounds for the definite integral to find the area between these curves. So after that, I wrote down the integral to find the area between f of x and g of x, which can be seen here, which is the definite integral from 1 to 2 of the square root of x minus 1 dx minus the integral of 1 to 2 of x minus 1 dx. So using u substitution for the first integral, which is the integral from 1 to 2 of x squared square root of x minus 1 dx, I did u is equal to x minus 1, and then also du is just 1 dx, or du equals dx, because the derivative of x minus 1 is just 1 dx. So from there, rewriting the integral from 1 to 2 in terms of u, I just did the square root of u du, which can be rewritten as the integral of 1 to 2 of u to the 1/2 power du. And to find that integral, you have to first find the bounds in terms of u for this integral, because now instead of using x as our variables, we're using u, which is our creation, so we have to find the two bounds for that. So to do that, u is just equal to x minus 1, so for that you just plug in the two x values from the first integral, which is 1 and 2, which you can see here is just u equals 2 minus 1 is 1, and then u equals 1 minus 1 is 0. So those are the two new bounds for the integral in terms of u. So from there, you have to take the antiderivative of u to the 1/2, which gives you u to the 3/2 over, it gives you 2/3 u to the 3/2, which you can do by doing the property of, I think it's the exponent rule, where x to the n power, the antiderivative of that is just x to the n plus 1 over n plus 1, which you can see here, u to the 1/2 power plus 1 is u to the 3/2 multiplied by n, which is 1/2, so 1/2 plus 1, which gives you 2/3. From there, you take the integral from 0 to 1 for 2/3 u to the power of 3/2, which gives you 2/3 minus 0, which just equals 2/3. So there you found the area of the first function, and now you have to subtract that from the integral, or the area of the second function. So for this one, I just rewrote it as 2/3 minus the integral from 1 to 2 of x minus 1 dx, which can be written again as 2/3 minus, then I split the two integrals up to make it simpler, of the integral of from 1 to 2 of x dx minus the integral of 1 to 2 1 dx. So from there, you have to take the antiderivative of x, which is just x squared over 2, because x to the n plus 1 over n plus 1 is that, x squared over 2. And then the antiderivative of 1 is just x. So then you take the integral of it in terms of 1 to 2 for both values, which you can see on this next page. So from there, I rewrote it to 2/3 minus 2 minus 1/2. 2/3 minus the quantity of 2 minus 1/2 minus the quantity of 2 minus 1. So for finding 2 minus 1/2, you have to find common denominators, which is just over 2. So I did 2 times 2 over 2 minus 1/2, which gives you 4 over 2 minus 1/2, which is 3/2. And then for the 3/2, then for 2 minus 1, it's just 1. And then you can rewrite that as 2/3 minus the quantity of 3/2 minus 1, which is just solving the integral of x minus 1. It's taking the area of square root of x minus 1 minus the area of x minus 1, which can be shown as 2/3 minus 1/2, because 3 over 2 minus 1 is just 3 over 2 minus 2 over 2, which is just 1/2. So from there, again, you got to find common denominators for 2/3 minus 1/2, which is 4/6 minus 3/6, which is 1/6. So from there, using definite integrals, you are able to find that the area between the two curves, square root of x minus 1 and x minus 1 in the interval from 1 to 2 is just 1/6. Now for the second part of my project, I had to answer a true and false question, which is stated here. If f of x and g of x are continuous on the interval 0 to 1, then the definite integral from 0 to 1 is f of x minus g of x dx is the area between f and g on the interval 0 to 1. Now I said this is true, which can be proved on the second page using this theorem from chapter 5, section 1, which states, if f of x and g of x are continuous functions on the interval a to b, where f of x is greater than or equal to g of x for all x values in the interval a to b, then the area of the region in between the graphs y equals f of x and y equals gx between x equals a and x equals b is given by this function below, or integral, The area between those curves is the definite integral from a to b of f of x minus g of x dx. Now I used a graph to interpret that theorem, which I just took two squiggly curves, two continuous functions, f of x and g of x over a interval a to b, and showed how the colored regions represent the areas of the two functions. So for g of x, the area under this curve is in pink, it's just from the function line down to the x-axis, and the area of f of x is just green and pink together. So what you can see from this is that the difference between the f of x and g of x, which is the area between the two curves, is in green, because it's the difference between f of x's area minus it's the difference between f of x's area and g of x's area, which you can see here, which is this integral from a to b, a specific interval of this function minus this function, the integral of f of x minus g of x, which you can even write that in longhand of the integral from a to b of f of x dx, so all of the area of f of x minus the area of g of x, so the integral of a to b of g of x dx here, which is the same thing as the theorem, the integral of a to b from f of x minus g of x dx. And to prove this even more, just to send it home, I did this exact thing right here when I was solving for the area between the curve square root of x minus 1 and x minus 1. And instead of just writing the integral as the integral of from 1 to 2 of the square root of x minus 1 minus the quantity of x minus 1, I just did it in the longhand way. So I hope that proves why this statement is true, that if f of x and g of x are continuous on an interval a to b, and in this case is just 0 to 1, that the integral, the definite integral from 0 to 1 of f of x minus g of x is the area between those two curves on the interval 1 to 0. Thank you.